Welcome back, and thanks for tuning into another explainer video on electrochemistry. This time, day 2 of electrochem. We're going to talk a little bit about voltaic cells and how they work from a more quantitative perspective, as well as how equilibrium and Le Chatelier's principle tie into all this good stuff. So what you'll see pictured here is what's called the standard reduction potentials at 25 Celsius. What we mean by standard is actually one of those things is right here, that's 25 Celsius. We also mean if anything is aqueous, it's 1 molar, that's standard, and if it's a gas, it's 1 atm. So standard potential simply if everything's under very controlled conditions. It just makes the values easier to explain. That's what makes this little degree symbol that I just basically covered up right next to the E. If it's not under standard conditions, that little degree symbol no longer applies, and the voltages will be different than the standard values listed here. The main thing about understanding this chart is that anything that's listed at the top is really good at taking electrons. So anything kind of up here, very good at taking electrons. And anything that's listed at the bottom is really bad at taking electrons. So these things kind of down here are very bad at taking electrons, or what you could certainly think about them is that they are really good at losing electrons, but not really in the way that is depicted here, because all of these reactions are indeed reduction reactions, meaning that we're always here talking about whether something can gain electrons. Remember that reduction is a gain of electrons. All of these reactions, notice every single one has electrons as one of the reactants. So every single one of these is written as something that's gaining electrons. And some of these reactions, again, like these reactions up here, are really good at gaining electrons, and the ones down here are really bad at gaining electrons. So the way this chart works in a very simple and straightforward way is if I put any two of these reactions together, any two of them, one of them is inherently better than the other at gaining electrons. So any two reactions that I mix and match, I'm going to find one has a more positive value, and that's the one that's going to gain electrons. So, oops, let's change colors there. The more positive value equals gain electrons, and the less positive value is going to lose electrons. And because it's going to lose electrons, that means we're actually going to have to reverse the reaction when we go to write it, because it's not going to be going through the process that's listed here. It's going to be going through oxidation. So given any two metals, we should be able to mix and match them to figure out how this works. So let's look at an example of how these two things work together. Back to the first page, it's still maybe less marked up. Silver is pretty high up on the list. It's 0.80 volts. And zinc, again, is hanging out pretty far down towards the bottom down there at negative 0.76 volts. So if we... Okay, so let's say we've got the smaller version of the chart here. Let's say we just choose any two particular elements that we so desire. Let's say that we go ahead and we decide that we're going to use nickel 2+, and we're going to kind of have that with a piece of solid nickel, and we're going to mix that with zinc 2+ and solid zinc. So we sort of have these two things being mixed together. So we have 1 molar zinc 2+, 1 molar nickel 2+ mixed with sort of solid bars of those elements sitting in their containers, and we would set up our voltaic cell. So we would have we'd have the, let's say, the zinc here and zinc 2+. We'd have our container here, just to make it appropriate. Nickel 2+ is green. So there's nickel, and we would connect them with a wire. We'd add our salt bridge. Let's imagine somehow that the salt bridge is yellow. And off the reaction would go. But the question is, in what direction would it be going? What is the reaction, and how powerful is this reaction? So those are 3 questions that are worth spending a little bit of time on. So In what direction is the reaction going? In other words, we could also think about this as what is the flow, what is the direction of flow of electrons? The second question would be what is the reaction? And the third thing is how powerful is it? What kind of voltage is this thing going to generate? And we can answer all those things from this chart. So the first thing that we can answer from the chart is in what direction? Well, we'll note that we can find nickel here at negative 0.25 and zinc down here at negative 0.76. So nickel has the more positive value. So it's going to be the one that gains electrons. And that means that zinc is going to be the thing that loses electrons. And very importantly, that means that it's zinc, not zinc 2 plus, loses electrons. Why is it not zinc 2 plus? Well, two reasons. One, very obviously, maybe to me at least, and maybe to you soon, is that zinc 2 plus has already lost 2 electrons. There are no more to lose, at least not easily. And so zinc 2 plus is not going to lose electrons. The other reason would be that we're reversing the zinc reaction. So the reversed zinc reaction, which we'll talk about in a moment, is going to be zinc becoming zinc 2 plus, kind of heading in this direction, not the zinc 2 plus to be zinc. So nickel is going to be gaining electrons from zinc. So if we were to indicate the flow of electrons along the wire, they're going to be leaving zinc. And imagine these were good arrows, and they're going to be heading to the nickel side. Okay, so that would be the answer to question 1. The answer to question 2, what is the reaction? Well, we're going to leave the nickel reaction the way we have it listed. So nickel 2 plus, leave a space, draw an arrow, draw nickel. Technically that's solid. This is aqueous. They don't usually do a whole lot of that on the AP test, but it is important certainly to note for reasons that we'll discuss. The zinc reaction is going to be reversed. So instead of, again, zinc 2 plus and zinc, we're going to have solid zinc on the left and zinc 2 plus on the right. And you may note, if you remember things that we learned way back in August and September, this is just a classic single replacement reaction. Zinc is taking 2 electrons, nickel 2 plus is taking 2 electrons from zinc, it's losing them to the nickel 2 plus. And rather conveniently in this case, the number of electrons that they're exchanging is the same. Nickel 2 plus is gaining 2, zinc 2 plus is losing 2, so we actually don't need to balance this reaction any further than we do because it was already all balanced. So that's the reaction. You take the thing that has the more positive value, leave it, the thing that is less positive, and reverse it. All you might need to do, and maybe we'll look at an example of that in just a moment, is if they're not one-to-one, you might need to adjust stoichiometrically to double or triple something else to make sure that the reaction balances, but you probably know to do that from the many net ionic equations that we've done. Okay, the third thing that we want to talk about is how powerful. What kind of voltage does this thing generate? So again, voltage or volts are really a measure of what is the difference in the strength of the pull on electrons. So how much better is nickel at taking electrons than zinc? The most powerful battery we could make from a voltage perspective, and power actually comes from both volts and current, we'll talk more about that in the coming days, but the most powerful one we could make according to this chart would be to match up lithium and fluorine, because then we'd be generating the biggest gap in gaining and losing electrons that we could possibly have. So fluorine is the best element at gaining electrons, lithium is the worst, or F2 is the best, and Li plus is the worst, technically. And so because we'd be mixing and matching the two biggest differences between the two, we'd get the biggest voltage out of it. So we're simply going to be comparing the two. And there's two ways of thinking about this. One is thinking about it from that E of the reaction. So the overall value of the cell is equal to E of the cathode minus E of the anode. If that seems kind of troublesome, because then you'd have to identify the cathode and the anode, you could also simply say that you could take the value for the one that's reduced and subtract the value for the one that ends up being oxidized. In other words, reverse that value. So for nickel, we're going to leave it as is, negative 0.25 volts, and we're going to subtract negative 0.76 volts for the zinc. And that will give us a value of positive 0.51 volts. until questions get sort of tricky, you should never ever get a value that isn't positive, because if you don't, you've done the reaction backwards. So if you get a negative voltage, that's implying that the reaction is actually running in the reverse direction from the one that you have constructed, and that's usually not a great sign. So you're going to get a positive value here. So again, we take the value that is more positive, leave it as is, and we reverse the value. Now we're reversing the value, right? We're doing this and this and this, because that second reaction, we are writing it backwards, right? We're doing zinc to zinc 2 plus, and because we're changing the reactions, reactants, and products around, we change the sign, as we do for so many things like enthalpy and whatnot. So we're changing the sign as we do that. All right. Look at our chart here. So a couple things that we would want to talk about relative to that reaction from a more equilibrium and Le Chatelier's principle sort of behavior. So let's think about nickel 2 plus solid zinc making nickel solid plus zinc 2 plus, and we're going to essentially figure out, we know that the voltage is 0.51, so that's the standard voltage. But there's lots of ways that this thing could be not standard. And there's lots of ways we could modify this. Now, it's a little weird to think about this, but luckily we don't need to do the math of it. The math of it is called the Nernst equation. So non-standard voltages, you can use the Nernst equation. That used to be a part of the AP curriculum. It's not anymore, of course, this year. None of this is a part of the AP curriculum, but it's still very important to know. The idea is, what if the values aren't 1 molar? Or if it's gases, what if they're not 1 atm? Or what if the temperature isn't 25 Celsius? What would happen? Well, a key idea about this is that even though we're writing the reaction as though it's not an equilibrium reaction, it is proceeding towards equilibrium. And the idea is simply that because the products are heavily favored, in a sense, they're almost unilaterally favored. Like we get pretty much 100% products and no reactants. The K value for this reaction would be enormously high, as we'll talk about in the coming days. The products are heavily favored, so the reaction's moving towards equilibrium. And in fact, the rate of reaction of the forward reaction is so much faster than the rate of the backwards reaction that we just draw a forward arrow here. Now, when will the rate of forward reaction equal the rate of the backwards reaction? Well, we'll equal it when the rate of the forward reaction gets to be so small as to pretty much be non-existent. So we reach equilibrium when the forward reaction rate is pretty much 0. In other words, an electrochemical reaction like this reaches equilibrium when it's a dead battery. So when the battery is dead or very close to being dead, now we have equilibrium, because a forward rate of 0 equals the backwards rate of 0, because the reaction really doesn't go backwards. Batteries don't magically recharge themselves. You have to plug them into outlets or generate solar electricity or whatever to recharge batteries. Batteries move in one direction. They do not move in the backwards direction, that we'll talk about in a couple days. But the only way to make this then achieve equilibrium is to essentially say the forward rate is 0, the backwards rate is 0. Hey, those are equal. We're at equilibrium. So Le Chatelier's principle sort of applies here in a sense that I can tinker with two things, the molarities of my two aqueous things. So I can mess with the molarity of nickel 2 plus or the molarity of zinc 2 plus. I can't do much with the solids because they're solid, and solids don't really have much of an impact on equilibrium. So in a Le Chatelier's principle sort of sense, if I increase the molarity of nickel 2 plus, well, now I have more of my reactants. If I have more of my reactants, the reaction moves even more to the right. If it moves more to the right, you get more products, and volts are one of the products of this reaction, so the volts will go up. Anytime we're going to move more to the right, we're going to get more volts. Another way to achieve that same effect, instead of having more reactants, is to have fewer products. So an easy and actually rather cost-efficient way to go about this is to just simply reduce the amount of product. Why do I need to have 1 molar zinc 2 plus? I can pretty much have no zinc 2 plus in there. I don't have to waste any zinc 2 plus, and if there's no zinc 2 plus, the reaction moves very heavily to the right, and the volts also go up. And you could, of course, do both of those things. From the reverse direction, I could also increase the molarity of zinc 2 plus. I'm not sure why you would want to do this, but if I increase the amount of one of my products, the reaction would shift back to the left and the volts would decrease. I could achieve that same effect, and in fact that effect happens all the time. Both of these do, as we'll discuss in just a moment. If I reduce the molarity of nickel 2+, then the reaction also moves back to the left and the volts go down. Both of those things happen as a battery runs. So as a battery operates, the volts drop. Right, the battery essentially gets weaker and weaker and weaker as it runs because the tendency is to move less and less favorably to the products. You don't move as rapidly to the products, and so the amount of volts that you get is decreasing because the amount of reactants are decreasing, the amount of products are increasing, the reaction rate is slowing down because with fewer reactants, the reaction slows down. It's just a simple rate law kind of thing. And as the rate slows down, the voltage slows down or gets decreased as well. And it's not a linear function. The Nernst equation sort of models it in a logarithmic way. So the voltage kind of hangs out and holds out for quite a long time. There's a very minimal decrease for quite a long time, and then it drops off rather substantially. Many of you have probably used calculators that seem to hold out for weeks or months at a time and then suddenly tell you that the battery is low and then suddenly don't work the next day. That's sort of that big drop-off that they're going to experience. So Le Chatelier's then has sort of a big effect on this whole thing. So we'll talk about that more in the coming days. Just the one last thing I just want to introduce, although again, I don't know that it's all that important, is simply, what and take do about a reaction that might be something that is not stoichiometrically one-to-one. So what if we did something where we mixed Ag plus and Ag with zinc 2+ and zinc. So what if we match that reaction up? Well, we can go back into account. We're going to have a couple things to then deal with. One is simply the fact that Ag plus is going to take electrons because it has a more positive value. It's 0.80, positive 0.80. This is negative 0.76, so this will take electrons. This loses, and so we have to reverse this reaction. So that means we're going to be having Ag plus on one side, Ag solid on the other, and then these get reversed. So we have zinc solid on the left and zinc 2+ on the right. But those are not stoichiometrically equivalent. Zinc plus is only gaining 1 electron, zinc is losing 2. So we end up needing 2 silvers to make that work. That's important from a balancing equation standpoint. It has no bearing on the standard voltage. Right, the voltage would still just be the normal 0.80 volts minus a negative 0.76 volts. We do not double that. We don't double it just because there's 2 silvers. The voltage really, in a sense, is almost like the potential for the very first electron to make its way from zinc to silver, and after that the voltage starts decreasing, so that the standard value cares not about the stoichiometry. What the stoichiometry will affect is how many electrons are going, how long the thing can hold out from a stoichiometric sort of mole ratio limiting reagent perspective, but it has no bearing on the potential of that reaction to happen at all. So that potential is entirely based on the nature of the elements, not on the stoichiometry of it. Okay, sorry for this one being a little bit longer than some of the other ones. We'll do some sample problems in the next couple of days and talk about some math a little bit more. But feel free to go back over this one, send me questions, etc., and we'll talk to you the next time. Thanks for tuning in.